if we are running from point A to point B, okay, point A is right here, point B is over here. If we run in a nice straight line, okay, we'll get there when we get there, right? But if all of a sudden there's a wall that we have to climb over, and then there's this pit of mud that we've got to crawl through, and another wall we've got to climb over, this pathway is going to take more energy to get there. The distance doesn't change, but it's providing us more resistance. Okay, it's going to slow us down, right? So when we're talking about resistance, we're talking about electrical resistance. We're talking about specific materials that are going to slow down the actual flow. So instead of it being from point A to point B, it's going to be here, and then something's going to happen here to slow you down, and then you're going to get to where you want to go. Okay? So when we talk about different factors that affect resistance, there's things that in the world of electricity, there's some things out there that are going to make resistance greater. Now, this little table on page 153 of your book, okay, is fantastic because it gives you some nice examples here. When we talk about the nature of a substance, a poor conductor is going to resist current flow more than a good conductor. It's going to be harder for electricity to get through something that does not conduct as well than it is as something that conducts really well. So one of the prime substances that we use for this is carbon. Carbon on your lab was an electrical conductor, but it is not a very good one. Okay, that's what makes carbon a metalloid. Now carbon, all right, will actually, as the energy is going through the wire, it's nice and great, that's metal. It hits the carbon and it slows it down. And then once it leaves the carbon, it speeds up again. It takes on its regular, the regular rate of flow. Okay? So the nature of the substance is very important in determining a resistor. Metalloids will flow more slowly than metals will. Okay, so metalloids are used as resistors. Now, the next one, so this is the substance. All right, so we've got substance. Now, the next thing we're going to talk about is the length. Length of a wire can actually add resistance. Think about it this way. If your wire is this long versus your wire being this long, okay? And if I say in the first, this is A and this is B, this is A and this is B, which one is going to take longer? The lower one, because it's longer. It's plain and simple. It's providing more resistance because there's a greater distance to travel. You're still getting from point A to point B, but just point A and point B there's more space in between them. Okay? So the length of the wire, the longer the wire, the higher the resistance. Okay? The next thing we're going to talk about is the diameter of the wire. So if we talk about diameter, I want to make the analogy of a hallway, okay, or traffic. Traffic's a perfect example, actually. I go home on Highway 20. And Highway 20, when you leave Montreal, when you leave the downtown and you're going west, there's 3 lanes, okay? There's 3 lanes of traffic. It's awesome. Then all of a sudden, those 3 lanes turn into 2. So what do you think happens at that merge? So that bottleneck that ends up being created, it's like we're changing the diameter of the road. So if you have a larger diameter, more energy can flow through. Less resistance. Okay? Less resistance than if you have a smaller diameter. You're forcing more energy to kind of wait its turn to try to fit through a smaller space. That's going to create greater resistance. Does that make sense? A lot of this is very logical. It is. Okay? But to just understand, if I throw the word at you and I say, how is length a factor in resistance? You're just like, I don't know. You actually do know this. It is quite logical. You can think your way through this. And then finally, temperature. So when we actually want to measure, like we understand the theory behind resistance, but when we actually want to measure resistance mathematically, if we want to calculate the amount of resistance that a light bulb is providing in a circuit, we can do that. Okay? And in order to calculate the actual resistance, we use something called Ohm's law. Now, Ohm's law states that for a given resistance, for a certain amount of resistance, the potential difference, okay, in any electrical circuit is going to be directly proportional to the current intensity. What does that mean? And again, here we're going to start to see some variables that we've seen before. Okay, the formula for Ohm's law is a pretty simple one. V is equal to IR, where V is potential difference, volts, I is current intensity in amperes, and R is resistance in ohms. Now the symbol for ohms, okay, is the omega. All right? Now, if we look at this, what we mean by that, when we say that something is directly proportional, if I rearrange this formula for resistance, I'm going to end up with R is equal to V over I. And if I look at that, at the definition of resistance, it says that the potential difference in a circuit is directly proportional to the current intensity. If you're looking at proportionalities, okay, you need fractions. Well, look at this. If the voltage is going to increase here, okay, if let's say this number increases and this number remains the same, okay, if voltage increases and current intensity remains the same, what's going to happen to the resistance? What's going to happen if this number, so let's say I have R is equal to 1 over 1, okay, 1V over 1A, right? What happens to my resistance then if all of a sudden I double my volts? If I say 2 volts over 1 amp, what happens? Does the resistance go up or down? It goes up. It gets bigger. Okay? Now, let's do the opposite of that. What happens if my voltage stays the same, but my my current intensity goes up? What's going to happen to my overall resistance? It's going to go down, right? So in this case, it's going to go down. So the symbols for this are ohms. So this is going to be 0.5 ohms, and this is going to be 2 ohms, correct? So when we do this mathematically, an example of a problem could be, you could be given, if I gave you Q, and I gave you T, and I gave you V, and I wanted to know what R was, and you only had Q, T, and V to go on, what could you do? Think of the 3 formulas so far that we have learned. So if we remember that I is equal to Q over T, okay, delta T, we remember that V is equal to Q over E, E over Q. Let me undo that. E over Q. And we remember that R is equal to V over I. If I'm telling you that I've given you in a word problem Q, T, V, and I want you to find R, is this going to be a 1 or a 2-step process? Is there any formula there that has Q, T, V, and R in it? Not one formula. What formula has Q and T in it? Current intensity, absolutely. So if I use this number 1 here, I'm going to get my I, aren't I not? Then what formula can I use to solve for R?
The bottom one, because you already have
The resistance formula, because I'm going to have my V, I'm going to have my I, and I can find my R. So this is what I mean by you need to know the variables that you're given. You need to understand what they mean, because you're going to have to do these multi-step processes. Okay?